Okay, I want to answer some questions before I even get them. So, this is on the Browning Mark IV Nightmare PLL synthesizer circuit replacement. The customer has given me the thumbs up to do it, to get rid of that nightmare of, the worst PLL design in history. And we're going to be sticking in this modern DDS VFO. Now, I've already had some questions, and if I don't get an answer to you, if you message me or something, I can only do so much, only so many hours in a day. So I'm going to try and answer some of those questions. For starters, some people were asking, is the signal going to be clean enough? Well, actually, this little thing it has don't get me wrong, it has lots of harmonics, but as far as noise that we'd be concerned about, basically below our the frequency we need, and maybe slightly above or something, there's really nothing there. So it's hooked. I have the outputs just terminated into a small inline 50 ohm 2 watt termination right here. So it comes out out the SMA connector to a BNC adapter into the 50 ohm termination, then that comes out, and I just have it run up to the spectrum analyzer there. And I have the span set from 0 to 60 megahertz on the far right hand side. It is outputting a, because I've already programmed the little module, so I have it outputting the frequency that I would need this to work at. So for channel 1 in the Browning Mark IV, the synthesizer or the PLL circuit would generate a 21.320 megahertz signal. So that is the peak right there. And then the next peak is going to be the 40, 2 times that, because that's the second harmonic. So that's going to be, 42.640 over there at that second peak right there. So, which you can see, there's really nothing there for, there's a little bit of noise down there, but that's no dirtier than the oscillator signals coming out of most of those circuits anyhow. Next thing was, but it's a DDS generator, so it's going to be a square wave. Well, no, actually this thing actually works really well, and it has a built-in amplifier, because this has a low and a high stage. I currently have it set into the high output, because that's what I'm going to need to use in this, because this is a tube-type radio, so it needs a higher, synthesizer drive than a modern solid-state radio would need. And all that this board does is, the difference between the low and the high is when it's in the little jumpers in the low position, the amplifier transistors are just powered off the onboard 5-volt regulator on it, and if you move the jumper over to the high output positions, what that does is it just connects the output transistors straight to the incoming 13.8 volts. So you can't run this thing over 13.8 volts when you have it in high drive, because then you stand a chance of burning it. I mean, even if you did, it wouldn't be a biggie, because the transistors are just 2N222s. So they're not even a dime a dozen probably. You buy those in bulk, you can get those things dirt cheap. But so, like I say, I have it in high drive. So let me switch from the spectrum analyzer down to the scope. And that's what the signal looks like in the high drive. So it is a slightly deformed waveform, no doubt about it, but that's no worse than I see in a lot of radios coming out of a synthesizer, so especially in tube-type equipment. So actually that's not that bad. And then it's actually, when you put it in a low drive, which I'm going to do, and to do that on these, all you do is, get her flipped up here, is take this little jumper right there and move it over to the other 2 pins. Oh, if we look back up at the oscilloscope now, you can see the signal has pretty much disappeared. So you can see there it is, and it's even cleaner like that. Almost kind of a sawtooth, but it's still a waveform. And as far as this radio is concerned, it should work just fine. Now I currently have it programmed, and you can program this thing for anything because it covers up to, it'll output up to 60 megahertz. But I currently have it programmed to where it would cover basically just the 40 channels just right now for, demonstrations. So you can see if I rotate the knob to the left, it doesn't go any lower than 26.965. And I rotate the knob to the right, it goes no higher than 27.405. And when I have the offset already set in this, so when the display here reads 27.405, the actual frequency coming out of the SMA connector there is actually a 21.760 megahertz signal. So that what you're doing is subtracting the the IF, which in these is 5.645 megahertz. Now other people have asked about, this is a sideband radio, what are you going to do about the sideband offsets? I don't have to worry about that. I actually was thinking about that earlier, and it dawned on me, I don't have to worry about that in this radio. The PLL, the output of the PLL module in the Browning Mark IV has absolutely nothing to do with sideband. When you change modes from AM to upper or lower sideband, the PLL synthesizer circuit in these radios is putting out the same exact signal. It never changes. I can show you on the schematic here. So basically on, I don't know where'd my pointer go. Basically on here, this is the coax cable, would be the BNC jack, comes off of the PLL module. The signal comes up and comes up here. Your sideband offset is actually done with the 5.645 oscillator. So here's the 5.645 megahertz oscillator. And in AM mode, and then here's your balanced modulator, your diode ring, so this is the balanced modulator. But in AM mode, it comes out of the 5.645. In this switch position, the AM position, it completely bypasses the balanced modulator. And then when it comes over here, you can see here's our, because remember this radio has two crystal filters. Unlike most radios, you only have one crystal lattice filter. This one has two. It has a separate crystal filter for lower sideband and another crystal filter for upper sideband. So that's where we get our offsets from. So this crystal generates the frequency in sideband. So in lower or upper sideband, both of those go through this balanced modulator. That removes the carrier, and now you're left with an output from the balanced modulator of a double sideband coming out of this. And then that double sideband signal is pushed through either the lower or the upper sideband. And that filter then removes the other sideband. So if you're in the upper sideband, it removes the lower sideband spike, and if you're in the lower sideband mode, it removes the upper sideband spike. So you only have one of your sidebands coming out, and then that is where the signal comes up from the PLL module, and they're mixed in this first mixer here. So we don't have to worry about sideband offsets. That's a completely different circuit. That's done with the 5.645 oscillator and balanced modulator circuit. It has absolutely nothing to do with all of this down, here. So it actually should be fairly simple. So it's basically nothing to it but to do it from what I'm seeing here. So I need to order a few things. I need to order a window to go around this, because the customer said he would like to have this, because he asked me, he said, is the channel display in the radio going to work anymore? I said, no. He said, well, if it's not going to work, just mount the damn thing. Just cut the hole bigger and mount it in the radio. Because that was one of the things I'd asked, because me personally, I hate cutting up radios. I don't, especially old classic collectible radios, because I'm a classics collectible collector. So, it just, the hair on the back of my neck and, stands up, and I cringe, and I get the shiver down my spine anytime a cutting instrument comes in close to a radio. But, like I had said in the previous one, oh man, this radio, the PLL circuits are just so archaic in these things. this might be the one exception to where it's acceptable. Now, a lot of people, and I don't know why I didn't think about it. I think I was just so frustrated the day that I made that video about, and I thought about using this. I didn't even think about it because I do that with other stuff. Just put it in a project box. So, if you were to do this in a radio where you don't want to go enlarging the hole for this window size, you could just put this in a project box, have an SMA jack on the back of it, run a coax cable with an SMA on the back of it, and then install an SMA jack on the back of the radio, the back of the transmitter, for the interconnect. And that's basically all you'd need. Other than you'd need to run power cables out to this, a positive and a ground, it doesn't need anything else. Because this is hooked up, for starters, to the transmit circuit, or in the transmitter, this has nothing to do with the receiver. Because remember, the receiver is a completely separate unit in the Browning Mark IV, pretty much like all the Brownings. It's a separate receiver and a transmitter. The receiver has its own oscillator. That's the the manual VFO in there. So the only thing we have to worry about is transmit. So basically, all I do is, so instead of it having a little RX for receive here, I would just jumper a lead on the one pin that puts it into the transmit, because you can set these up for different offsets for receive, transmit. It even has a repeat. Because remember, this was designed for ham radios, so this thing even has repeater offsets you can set up. But what I can do is just run a jumper over to the pin that puts this into transmit mode, so it just stays in TX all the time. But yeah, it should be basically as simple as cutting a hole, popping this thing. Well, actually, the first thing, it's going to take longer probably to remove all the crap out of that transmitter. But the first thing I want to do before I do anything is before I disconnect or cut anything on that radio, what I want to do is just basically unhook the BNC cable, hook the BNC cable up right here basically, and try and operate the radio using this. Basically what you see right here, just disconnect the output from the PLL that's currently on the radio and hook that coax cable up to this VFO and see if it works. Like I say, I think the drive level should be fine, and I don't foresee any problems. Like I say, I just need to order the trim ring, so I'm going to cut the hole. But once I can verify that this will, it's that simple. It'll just be a matter of cutting the hole, removing all of that crap out of there, all three, the two boards behind the channel display, the actual display board, the board behind that, the PLL, shielded can, which somebody Swiss cheese. That thing, my God, they must have drilled 20-some holes in that thing to ventilate it. Well, yeah, that's really good. They put it in a shielded box for a reason, and it's now Swiss cheese. That was another problem with that thing that I forgot to mention. Somebody turned a can into a piece of Swiss cheese. But, once I get all of that out of there, all I need to do is pump 12 to 13.8 volts into this thing. I can remove all of the regulators in there. Now, what I might do is actually put a 12-volt regulator in it. I will probably do that just to clean it up a little bit, because I needed, hook up a scope to the voltage that's being supplied from the receiver, which has the power supply in it. See how clean that is. Maybe add a little bit of filtering to it, and I'll probably stick an onboard 12-volt regulator inside the transmitter, and then the voltage that goes to this will actually come off of that regulator. I just, just to be safe, because, this is modern. It's not going to like high voltages, and just to prevent any spikes or anything, just basically try and use the regulator as a buffer between that high voltage circuit, and you never know what might come through that, and this. Well, I mean, that's what they did in those radios. They just, instead they had a 5-volt regulators and whatnot. I'll just be using a 12-volt regulator instead. So, well, I think this is going to work. Like I say, it should actually be fairly simple. I've already got this programmed for the CB channels, so it covers. So it should just be a matter of popping the thing in there, and it should work. So I just thought I'd give an update. Like I say, I wanted to show what it actually looks like on a scope. That yes, it's not a square wave. And like actually Mark pointed out, since this is a DDS VFO, it's not a sine wave and it's not a sawtooth, what it looks like. That's actually an infinite number of square waves. So if you were, now this scope can't zoom in far enough, But if you were to keep expanding that out and expanding it out, you'd eventually get to a point where you'd see a bunch of tiny little square waves. That's actually what those, sine waves are comprised of. Billions or trillions of little teeny tiny square waves, because it's a DDS, and the DDS VFOs that's what their output actually is a square wave. It's just done so much that it's, by the time you get done cramming all those little square waves together, basically, you end up with what looks like kind of a sine wave. But like I say, it's the output looks good. The mixer circuit, the spurs, when I had that hooked up, and I can hook it back up to the spectrum analyzer, like the second harmonic, I shouldn't have to worry about that at all. The second harmonic is going to get, because once it goes through the mixer, all of that's going to get filtered out. Once it through the output, because it's, like I say, man, this should actually be a really simple installation if things go as planned. So, now granted, most of the knobs on that transmitter will become useless because the only thing this needs is this one little knob right here. That's all. I just put this knob on here to make it easier for me to turn it while I was playing with it here. But, I can move the cursor. Now, like I say, I currently have this limited to it goes no lower than 26.965, and I have currently the upper limit set at 27.405. But, when you push down, because this is also a push button, so if you push down and move it, that's another nice thing about this. You see how many, this is a true 8-digit display here, but you see I moved the cursor down to the last digit. So, for sideband operation, you can see you can actually do it in 1 hertz steps. So, or you can come over to, so if somebody tells you, oh, you're off frequency a little bit, you could adjust in 10, in hundreds, tens, or even, 1 hertz increments at a time, if you were so inclined. So, it's basically like having an unlocked clarifier. Using this, that's basically what you have, is an unlocked clarifier, more or less. But, so normally what you would do is, because you would have your cursor set right here. So, it'd be 27, channel 40, channel 39, channel 38, 30, and so on, because you'd have it changing it at 10 kilohertz at a time, which is the CV channel spacing. But, like I say, man, this little thing should actually work out really well. I don't foresee any problems. I might make an enclosure for this. I don't know. I just need to, I'm just wondering about maybe stray RF energy in the radio coming up in and maybe mixing in. But, this was designed to be used in old tube radios. So, and I know they work fine in, like Yaesu FT101s. So I don't think there'd be any more stray RF energy in this Browning than there is in a Yaesu, on the inside. So I think it should be a straightforward installation. So we'll see. Like I say, I need to order a few things. Probably what I'm going to do is I'll leave the SMA jack on this just for serviceability. That way, if this ever needs to be serviced, it'll be basically disconnect the 2 wires off that header there, unscrew your SMA jack off of it, pop your little plastic bezel that will be on the outside off. You can just unplug the wires from the rotary encoder off of the board. So you could even leave this in the radio, and you just take off your 4 screws here, and then you could just remove the entire module. So like I say, that should help with ease of serviceability if it would ever need to be serviced. But like I say, what I'll do is I'll just run because I don't know if actually it might be. That's another thing. I'll need to check the length. The BNC cable that's in that thing might be long enough. I might be able to go straight from. Nah, I'll probably run a new one. Yeah. Because I'm just going to use the smaller diameter. I'll use a piece of Teflon, really high quality coax cable. So what I'll do is I'll just pull a chunk of SMA cable out that I have, put a new SMA, a female SMA connector on the end of it, so I can attach that on this end, and then I can just solder the other end in where I disconnect the the other beans or the other coax cable in the radio. So there you go. There's my thoughts on, you know, basically what I'll be doing. So, you know, in a nutshell, you know, everything from basically this line down is going to disappear. Literally everything. All this power supply circuit, because this is the low voltage power supply circuit that feeds all of this mess, and then all of this mess will disappear. So everything down here, you know, basically from the tip of this pointer down, as I go across, all of that is going to go away. So we'll be left with only the vacuum tube portion of the radio, and then that little guy right there will replace it. So there you go. There's my thoughts, and like I say, I'll get a few little things ordered I need to install it, and at a later date you'll see this. Like I said, I'm going to try it out first, but as long as it works, it's just going to be a matter of sticking it in there, and I'll when I get it, if it does work out fine and I get it installed, you'll see what it looks like when it's done.